Hi, I'm Joe Hellerstein from UC Berkeley. I'm going to speak today about sort of passion of mine over the last over a decade now, something I've been working on, which is how are we going to program the cloud. And this is a talk in about 5 chapters that I gave in an hour talk. And so we'll take a few chapters, and probably not all of them. We'll probably get through the first 3 or so. So I'll start by talking about serverless computing. This is joint work with a number of students and postdocs at Berkeley, and based on a paper we had at the CIDR conference earlier this year that created a bit of a stir, a bit controversial. So, you know, when you look back, or at least when I was taught the history of computing, because I'm really only 14 years old, you know, you go back to the 70s, and we had sort of from the mainframe era, we had this series of kind of different generations of compute. And for each of them, they sort of came along with a programming model that was endemic to the environment. And there's sort of a narrative, especially from the sort of Unix mini computer era, but it's carried forward, that a new computing model only really comes about with a new programming model that meets that computing model. So the marriage of C and Unix is often told, that story is told in operating systems classes around the world as this kind of legend of how you really approach the computer differently through a different programming model. And arguably you can say the same thing about supercomputers, about things like personal computers, particularly with graphical interfaces, and about smartphones and so on. So, you know, generations of computing, each with their own different programming models and languages. So here, suppose I offered you a computer that was actually 1 million computers, right? And most of the world's storage. Well, of course, this is kind of true. You know, these are sort of some wild guesses based on statistics that are out there, but, you know, order of magnitude here and there, give me some slack. AWS is something like 10 million servers if you sort of do the arithmetic on what they've published. And you can also read on storage industry that something like a half of all the bytes that are being generated in the storage industry are being sold to what are called hyperscalers. So Amazon, Google, Facebook, and so on. Okay, so most of the world's storage and millions of computers are indeed available to you today. And there are examples, I think, on Google Cloud of folks doing mathematics on 500,000 computers. Okay, so it's happening. And really the big query, if you will, is how will folks program this new platform, right? In a way that fosters the unexpected innovation, right? It wasn't just that Apple shipped the iPhone, it was that there's an app for that, right? All these application developers were enabled and inspired to be able to build new things that you wouldn't have thought of before on these new platforms, okay? The thing is that, you know, programming the cloud's really, really hard. It's distributed programming. It's actually distributed programming with auto-scaling. So not only do you have all the problems of distributed computing that we all know about, parallelism, consistency, partial failure, but you have this thing which is that actually the hardest part of distributed computing, which is nodes come and go, that's actually a service to you now. That's a good thing, right? So it's sort of, they've taken hard and made it even harder as a virtue. And we like this. This is all good stuff, but how do we program it? Particularly we being normal developers, not superstar programmers sitting inside of Amazon, Facebook, and Google. And the prevailing answer is sort of the Linus answer, which is, oh, let's just not think about that and keep programming in Java. Right? That is actually how most, especially open source, distributed software is being built today. You know, Java is a language that was originally designed to run in your browser, if you remember back to the 1990s. And you know, it's been used now for server software, but it's fundamentally a sequential language in the classical von Neumann style, where you have a single thread of execution that's operating serially, mutating storage in memory, right? So I've been talking about this problem for like over a decade. You know, we actually generated a whole bunch of buzz about this like in 2010. We had a language that we designed called Bloom. We had a number of papers. We've been running around talking about this for a long time. And for the most part, people nodded and said, well, you seem very clever, thank you. And they went away and kept programming in Java. Right? And that's nice. And so time passes. Sometimes you're a little ahead of things. And the industry has awakened. All right? And they've started to propose a programming model for mere mortals, so to speak, to write programs on the cloud. All right? And they call it serverless computing. And it's sort of charming to me to see students at Berkeley get really excited that suddenly now they can do stuff. I wrote a machine learning algorithm and just uploaded it to the cloud and it ran. It's so powerful. You're like, well, it's like a totally local, no shared computation, really simple algorithm. So yeah, right? But like, what about the hard stuff, right? So serverless computing is hugely buzzy right now. It's buzzier than MapReduce at its peak. Okay, so if you lived through all that, this is all the buzz. What do they mean when they say serverless computing, the cloud vendors? Because when I talk to people who are enthusiastic about it, they get really slippery. They're like, oh, no, that's not serverless computing. That's just the beginning. Serverless computing will be all these other things. It's like, well, maybe. If you keep calling something X, but you keep adding things to it, is it still X, I guess? Right? But for now, let's talk about what actually is shipping, and we'll use that as our definition of serverless computing. All right? And so we'll go with what the vendors are selling, which is functions as a service. Okay, and this is typified by AWS Lambda, which is far and away the most widely used of these. And most of it applies to Google Cloud Functions and to Azure Functions as well. Although, I do get some pushback here and there from some of the vendors. So this is a snapshot as of last October. And this is a fast-moving space. And indeed, these are very capable vendors. And they are innovating. And they are still calling it serverless. So that may be what happens. That goodness is poured into this bucket, and then the bucket expands. And that's fine. And the thing I'd like people to focus on in the talk is kind of thematically what are the challenges. And we can call it what we will. Okay. So let's step back and ask, what are the promises really of this cloud platform? And arguably, there's really three key promises. Auto-scaling. So you pay for what you use. Right? If you have a big job, it should scale up and use lots of resources. And when you stop running that big job, it should scale back down and charge you for few or no resources. Okay, so sort of pay by the SIP, if you will. And all of the serverless products are very focused on auto-scaling, which I think is challenging and really good. Like, this is what the cloud is about. It's not just about big. It's about efficient, right? Efficient use of this infinite resource. It's about scalable data processing. There's absolutely no reason to use millions of computers for things if you don't have a lot of data. It's almost no applications need lots and lots of compute with no data. That's crazy. Okay, there may be a few scientific simulations and so on, but they're very niche-y. And then, of course, distributed computing. That's why we have thousands of computers, because one computer is not enough, right? So that's what the cloud's supposed to be good at. And I think what we see today with serverless computing is it's kind of one step forward and two steps back. So they really focused on auto-scaling, and they took away scalable data processing and distributed computing, which is kind of bananas. All right, but this is kind of where we are. So, and I think it's a very savvy and reasonable thing to do in the sense that, like, let's get started somewhere. We'll do the easy thing that's got the most differentiation, right? Auto-scaling actually with most services in the cloud today is poor. Okay. In fact, many of the things that have the prefix elastic in front of them in cloud products today are not elastic. They do not auto-scale. They can be reconfigured, which usually takes time, but they have to be reconfigured manually as your workload changes. So they need ops people to reconfigure them. So when you say elastiblah in a lot of cloud services, that's not really auto-scaling. So that's why I use the word auto-scaling rather than elastic. Okay, so here's three limitations of the current Faas offerings. This is certainly true of Lambda at the time we did the paper, and I believe it applies as well to Google Cloud Functions and Azure Functions as well. So limited lifetimes for your functions. Right before we wrote the paper, Amazon bumped from 5 minutes to 15 minutes. So your functions after 15 minutes will unceremoniously die, okay, which can be troublesome. The most difficult thing about this is not that things fail, but that the state that they have is gone. Right, this means that when you reconnect, when you talk to one of these functions, and it's been thinking about some stuff for you, and it remembers you, when it goes away, you can't reconnect to it. It's gone. Right? So that any cached context in these functions is gone. They have to start from scratch every time they're reborn. There's enormous I/O latency bottlenecks, 1 to 2 orders of magnitude higher than a single modern solid-state drive. All right? And of course, in principle, you should have all the storage in the world. I'm talking about a single SSD's latency, okay? And then there's no inbound network communication allowed with these functions. You can't talk to them other than by invoking them. You can say f of x and pass it x, but once it's running, you can't talk to it. It's pure functional in that sense. Okay, so let's see what these limitations lead to. Well, implication number 1 of all this is that the current Faas services are data shipping architectures. And this is like old database wisdom that I was taught in graduate school in the 1990s, okay, which is you should push your code to your data, not suck all your data out and give it to your code. This is just bad architecture because you are trying to push a large thing through a small hole. You should push the small thing through the small hole instead. So, you know, the Turing Award winners of database systems are not impressed with this architecture, right? So. Unfortunately, Jim Gray couldn't be at CIDR because he passed, but Mike Stonebreaker was certainly there, and yeah, he's not impressed. So we measured this. So we did a scenario. We tried to do a modern one, not an old-fashioned one. So we have a prediction serving project in the RISE lab at Berkeley called Clipper. Its job is to take models and deploy them and then serve predictions, right? So when you go to the website and it needs to show you ads, it does a very low latency prediction in this model to figure out which ads to show you. That's sort of the typical example of prediction serving. So we had the world's simplest model here, which was a classifier. It would strip the dirty words out of a message, right, by looking things up in a table of dirty words. World's dumbest model, right? So that's fine. The way you do it with Lambda is you go through their queuing service. The way you might do it is to just take a node at AWS, rent it, and deploy the model there. Okay, so our baseline is we take just a node at AWS. We use the built-in AWS services that are available to anyone. It's not auto-scaling, and it doesn't use the Lambda API. But it uses AWS machines that are the same as the one Lambda uses. And it's something like Lambda's 127 times slower than this solution and 57 times more expensive. So like you could be off by a factor of 50 in your deployment of hand-deployed machines and still be cheaper than using Lambda autoscaling, which defeats the whole purpose of autoscaling, which was to save our use of resources, right? So being off by 1 to 2 orders of magnitude is not a good thing. All right, implication number 2 is that you actually can't do anything interesting from distributed computing using Lambda. So this is, if you recognize it, a classic Lamport diagram. It's in fact the Lamport diagram from Lamport's famous paper on Lamport diagrams. It shows communication of coordinated processes over time and talks about causality, right? His definition of causality that happens before relation. So in Lambda, it kind of looks like this. You're not allowed to communicate, so we have to take out all the edges that represent communication. All right, and we replace them with putting things in Lambda's, or in Amazon's deep storage and pulling them back out. So that's either S3 or DynamoDB. Those are your choices today on Lambda, because those are the auto-scaling services that they provide for storage. All right, those things are really expensive and they're super high latency, particularly S3. So Leslie Lamport, another Turing Award winner now from Distributed Systems, also not impressed. All right. And again, we did some measurements. So just basic communication between nodes, if you do it the Lambda way with pure function invocation, it is 1,000 times slower than just having two EC2 nodes talk to each other over a network port. All right? And if you go through storage servers in the Amazon cloud, depending on which ones you use, it's something like 30 to 300 times slower just to round trip to storage in Amazon standard services. Nobody would build a distributed algorithm in this way. This is just extreme badness. All right, so we built one just for fun. So we took the simplest distributed protocol you can imagine, which is a leader election protocol. We used DynamoDB because that's the lowest latency communication medium they offer. And of course, after 15 minutes, lambdas die. And so if you're doing leader election, it's time to elect a new leader, or at least check every 15 minutes. And in that environment, we spent 2% of our time just doing leader election and nothing else. And that was in this sort of bestest of bestest cases, which I won't go into describing, but very generous. And this cost $450 an hour as a background task, all right, in this network. So really, again, it's not sensible or feasible to do distributed computing on this supposedly distributed computing platform. Okay. So serverless computing love the auto scaling. They've really dropped the ball so far on data latencies and on network communication. And we're in the process of designing systems in my group at Berkeley that will allow you to have functions and data co-located and allow you to have long lifetimes and allow you to have network communication and enjoy the benefits of auto-scaling on top of that. And so if we had time for the back of the talk, I would tell you more about those systems. We have a paper in process probably next month. We'll have some stuff up on archive. So the thing is that to get this right, we need to embrace state. We need our functions to be stateful. We need the data to be close to the functions and the functions to remember stuff. Okay? So local data that's managed across invocations. So for example, if you go back to the, say, web server that you just hit, it will remember your data and have it cached, or it will remember your session, or whatever. And if you're doing a proper algorithm, the algorithm can actually remember things across rounds. Yeah? So there's two sort of challenges to getting this kind of state in your functions. One of them is that data is expensive to move. And if functions are moving around, because it's auto-scaling, right? It's growing and shrinking over time. You have to move the data as you move the functions. And that's true. It is somewhat expensive. But actually, bandwidth in the cloud is amazing. All right, there's tons of bandwidth back there at Amazon. And the general assertion is this isn't that bad. We're all inside of Amazon already. It's not this sort of data ingest and egress problem to and from the cloud. It's within the cloud, possibly even within a single rack, and it's not a bottleneck. All right, so we could argue about this. I don't have data points today to support this, but basically that's not the big problem. The big problem is distributed consistency. This is the classic problem from distributed computing that we always have, which is when multiple nodes are running, they can't know instantaneously what each other thinks, right? And so they can make wrong guesses about what each other thinks, and mayhem can ensue. It's a known hard problem that simply we have to face, and we have to somehow surface to our programmers if we're going to have a distributed programming model. OK, so consistency, to just dwell on it a bit more, it's the idea of ensuring that agents that are at a distance agree or will at some point agree on common knowledge. It's that simple, all right? And the classic example of this, the one that's always used in these discussions, is data replication. So if we have a mutable variable x, and it's being updated in two different places, the two different places may have a different view on the current value of x at any given time, right? And if they disagree now on that value and they move forward, they may start disagreeing about more and more things over time. And so you get what's called split brain, right, where you have two different parts of the computation that really believe different things about the state of the program. And this can lead to all sorts of mayhem. And if you're doing it on persistent data, like database data, this can lead to persistent mayhem. And it can be very hard to clean up, right? So you can really get yourself into a permanent hole. So the classical consistency mechanisms, the kinds of things that kept Jim Gray and Leslie Lamport up at night in the 70s and 80s were these kinds of problems, consensus problems. So the classic Lamport protocol of Paxos, you get a fixed set of machines, fixed in parentheses because they didn't assume autoscaling back then, but get a fixed set of machines to choose the same thing. What they did worry about back then was failure. So you'd start with a fixed set of machines, and some of them might go away, right? So they actually, in some sense, did worry about the set of machines changing. The next step after Paxos is to get a fixed set of machines to choose the same sequence of decisions. And once you've done that, and schemes like multi-Paxos will do that for you, once you've done that, then you can do distributed computing, because you can move through a state machine together, right? So all the machines can execute the same distributed state machine, and they can therefore do a distributed computation in concert. And so the typical uses of this are state machine replication. Certainly that's the formal model that's in the literature for all the theory of distributed computation. More practically, what it's often used for is simply to make sure that I/O requests, writes to a database or a file system, are linearized. So that if I issue a set of write requests, the order of the acknowledgements is the order of the writes, yeah? The order of my requests is the happens before relationship of the writes. The other piece of this is commit protocols, which grew out of more of a database community. And the idea here is to simply get a fixed set of machines to agree on the outcome of a unanimous vote. So where Lamport and company are worried about state machines, database folks are worried about batch transactions, right? And the idea is that I want my transaction to all happen, and for all nodes to agree that it happened, or to not happen at all. So it's a bit more of a chunky set of computations. It involves the possibility that my writes are entangled with each other, and it's important that you don't just treat them as individual correctness criteria, but as a global correctness criteria across all the actions of the transaction. So it's a bit of a different problem setup. Serializability is a bit of a stronger concern than linearizability. In any case, this is typically used for serializability of transactions on these arbitrary rewrite programs. Okay? So this is great. This is known stuff. It's been implemented many times. It's tricky, but it's certainly doable. And this is the kind of thing that you can have your superstar wizards go build as a service inside of Google Cloud or what have you, and offer to customers. That's what database industry does, right? It does commit protocols for you on a distributed system. Probably Teradata was doing this in the 80s. Okay, so lots of systems have done this for years. Thing is, it's really not scalable. It's super slow. So that's James Hamilton. James is awesome. He started his career as an auto mechanic. And then he worked on IBM DB2 in Toronto, big database system. And then he moved to Microsoft, and they wouldn't let him work on databases, so he worked on file systems. So he worked on NTFS at Microsoft, got interested in containers and warehouse-scale computing, moved to Amazon, and is one of the key architects of AWS. So he's seen lots of different kinds of systems at the scale of individual components, as well as at the scale of warehouses. So this is from a talk he gave in the late 2000s, the first decade of the 2000s. And I like to present it formatted this way because I think it's beautiful. The first principle of successful scalability is to batter the consistency mechanisms down to a minimum. move them off the critical path, hide them in a rarely visited corner of the system, and then make it as hard as possible for application developers to get permission to use them. All right? Remember, this is the good stuff, right? Nope, you're not allowed to use it. Why? Because this stuff is very, very slow. Waiting for control is bad. If you've got a very large scalable system and you need to wait for a quorum, you will wait for the slowest person in the quorum, right? And you're now at the mercy of tail latencies. And anyone who's lived in sort of super scaled computing knows that tail latencies are death, right? There's always going to be something slow. When the odd, it's just probabilistic, right? You get a large population, there'll be something that's a straggler. The other issue, which is key, is if you're waiting, that's probably because you need to wait for somebody else. Somebody else is probably also waiting for you, and you get queuing effects, okay? So this problem is not just your problem. If you use this stuff and you're an undisciplined developer, you can screw up everybody else. And Lamport famously said, a distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable, right? This is the core of distributed computing. Okay, so we don't want to put this in the hand of junior developers or even of developers that don't want to focus on this stuff. They want to focus on their application, right? So they're not thinking about this all day, every day. So to get towards a solution, the key problem at some level is that the interface, the API to distributed computing has always been super low level. It's been reads and writes, right? And so there's this famous Far Side, right? What we say to dogs, Ginger, I've had it, stay out of the garbage. You understand, Ginger, stay out of the garbage or else. And Ginger hears blah, blah, Ginger, blah, 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 Ginger, blah, blah, right? So this is with credit to my student, Peter Bayless, this is what we do with databases and file systems. Okay, database, I'm going to increment this counter, take one iPhone out of inventory, queue a request to the billing service, and issue an email confirmation. And all we see at this layer is read, write, read, write. Right? We have no idea that there's mathematical things like incrementing, which we might know is commutative. We don't know that we're doing multiple systems. We don't know which of these systems needs to be consistent and which of them can be less consistent. Right? None of this is visible. All we see is read, write, read, write. So can we do better if we reason about application semantics? And this has been something that we've been doing research on in my group for a long time now. If we can lift these problems into the compiler, rather than leaving them at the I/O interface, perhaps we could do something much better. But that leads to a fundamental theoretical question, all right? Suppose we have the perfect language, and we understand everything about the programmer's intent, all right? I have such a language for you. I'd be happy to sell it to you, but let's ignore that, okay? Suppose you had such a language. Which programs could be correctly implemented in a distributed fashion in the James Hamilton style without coordination? You have a task. Can it be done without coordination, or is that impossible? And it's a computability question, all right? I'm giving you a language. It doesn't have coordination, let's say. So I've taken away the coordination pieces of my language. What can you compute? And what can you not compute? So that's a fundamental question that nobody ever asked before. And if you go back to, it's kind of crazy, you go back to the distributed systems literature and you sort of look at the motivation for why did they invent Paxos? And it's sort of like, well, because. I might have a race condition. And if I did, what would I do? It's like, well, why do you have a race condition? That question is not asked. All right, but when I think, the ML query talk, I was one of the founders of the MadLib project, and it's the same thing. It's like, well, if you force me into a funny compute model that scales super well to write machine learning algorithms, what machine learning algorithms would I write? Yeah? We're in this world, right? We want to be in this world. We need to answer this question. Okay. So I sort of threw this question out to the community in as best framed a way I could sometime in 2010, and the community came back with proofs, which was great. So the next thing I want to talk about is what we call the Calm theorem. Started out as the Calm conjecture. The next thing we'll talk about is the Calm theorem. So the hypothesis that I had was that those programs that you can compute without coordination are the monotone programs. All right. And by that, I was using a database person's intuition, and I've sort of elided these slides because it takes too long. But for those of you who are database folks, Kurt, I'm looking at you, we know blocking algorithms like group by block because they can't give an answer until they've seen everything. But we know lots of things don't block because they can be pipelined, right? They're streaming algorithms. Like, for instance, join is a streaming algorithm. Mind you, join as implemented in MapReduce and Spark is a blocking algorithm, but that's because those systems are primitive. Okay, but join and Teradata is a streaming algorithm because it's always been better architecture. And that's true of all the parallel databases. So that's an example where there's a task that you can implement in a non-blocking fashion, which is to say no coordination, or you can implement it in a blocking fashion. All right, so that one could go both ways. But there's certain tasks like not exists in the database that you can only implement in a blocking fashion. So why is the question here, right? And so my hypothesis is that anything that's non-monotone, and I'll give you a motivation for this, requires coordination. Anything that's non-monotone does not. So that was the hypothesis. I threw it out there. Now I have to do this. So let me read the theorem. A distributed program P has a consistent coordination-free distributed implementation if and only if it is monotonic. It's incumbent on me now to define consistent coordination and monotonic, right? Without that, this is like just a whole word salad. Okay, so I had a specific idea in mind. It's been sharpened by the people who wrote the proofs. So let's go through it. What do I mean by consistent? Well, here's the intuition, again, leaning on our friends at AWS. So that's Werner Vogels, former Cornell professor, now AWS honcho. So he defined this thing that they call eventual consistency in the storage systems world. And he defined it as follows. The storage system guarantees that if no new updates are made to the object, eventually all accesses will return the last updated value. That sounds nice. But I have so many questions about that. That's like very poorly defined, all right? So, just things like, why would you think that there's no new updates that are going to happen? And if new updates do happen, then what? How would you know that they stopped? And it's really last writer wins. So which one was last in a distributed system with distributed clocks? And what if there are ties? And what if different people have different perceptions of that? Like, what do you mean? All right? Oh, and by the way, that, right? So he's like basically saying this is true for reads and writes. So we're still dealing with this sort of like hammers and sticks kind of language for this. So can we define a consistency semantics that's got this flavor of being kind of relaxed, but that actually guarantees some application properties in some formal way? So that's the flavor we want is eventual consistency, but we really need to put some bones to this so that it's theoretical. So we're going to lean on something more formal from the programming language community, which is Confluent. All right, so the definition that we're going to go with is that a distributed program P is consistent if it is a function from sets to sets. Right, so you get a set of inputs, right, which are all the requests that come into your system. You produce a set of outputs, which are all the responses, yeah, that is deterministic in the face of non-deterministic message ordering and duplication. So the messages zinging around in the cloud, whatever order they go in, even if some of them are dropped and retried, and maybe they're received twice at the far end, okay, you still get the same answer. Right, so it's a Confluent program in the face of this non-determinism. So that's going to be our definition of consistency. All right, a function from sets to sets that is insensitive to the ordering and the duplication of messages. So to go back to the classic example of replica consistency with storage, we'll say that so we're going to raise this up, sorry. So this example, we actually not are replicating just data, we're going to replicate programs. So I'm going to run the same program P in two different places, say for fault tolerance, and I want them to agree on the outcome of the program as long as they get the same set of messages. Right? So I'm going to run P twice. They might get the messages in different order, but no matter which one of them I choose to get the answer from, that'll be the same answer. Similarly, if I run P today and I run P tomorrow, right? If I give it the same set of messages, it'll give me the same answer. All right, the second definition we needed was monotonicity. This is classic. So, a distributed program P is monotonic if for any input sets S and T, where S is a subset of T, the output of P on S is a subset of the output of P on T, right? So another way to think about monotonicity is if you take an input and you add some more stuff to the input, you only get more stuff in the output. Particularly, and this is a really good intuition, as you add stuff to the input, you never have to retract something that you previously output. So that means that you can do this kind of progressive results, right? Your program can start emitting results right away if it's monotonic because it knows that no matter what comes in, everything that you've already decided on is true. This is actually the sort of crux of the intuition for why this is the stuff you can do without coordination. I don't have to ask anyone else if the output so far is correct. I can just start emitting it. I know it's correct. It's a monotone function. Anything I know is true will remain true. Right? All right, so that's going to be that's the crux of the intuition at some level. Finally, what is coordination? What counts as coordination? What are we going to rule out? Okay? What is the stuff that's making James Hamilton crazy? So a distributed program P uses coordination on an input T if it requires messages to be sent in the network under all possible input partitionings of T. So it doesn't matter how you lay out T to start. You'll still need to communicate. Even if you put all of T on one machine, it's all there. You still need to communicate. Then you're coordinating. That communication is called coordination. Let me give you an example. Two examples, actually. One that requires coordination and one that doesn't. All right, so the first example, classic distributed systems problem, it's distributed deadlock. So in databases, there are these lock tables, and processes might have to wait for other processes. So a transaction T1 might be waiting for transaction T3 on machine 1. And on machine 2, we know that transaction T5 is waiting for T6, and transaction T3 is waiting for T1. And on machine 3, we know T4 is waiting for T1. And one of the tasks you do in a distributed database is you say, are there cycles in this waits for graph? Because if there are, that's a deadlock. The people on that cycle will never make progress. They're waiting for each other, right? But to detect that deadlock, we're going to have to ship these little edges around to somewhere, maybe to everywhere. Maybe we gossip them, or maybe to one place. But we're going to have to ship them around and look for cycles. Because as you see, nobody currently sees a cycle, but there is one. It's T1 to T3 back to T1. OK, so suppose machine 1 and machine 2 chat. And machine 2 says to machine 1, I have T3 waiting for T1. Machine 1 will say, aha, there's a cycle, right? And they will never have talked to machine 3, but they'll be right. Yeah? And in fact, if it had turned out that the graph was partitioned differently, and that T3 to T1 edge was on machine 1 to begin with, there would have been no communication, right? So this is an example where the communication is for solving the problem. The communication is not for coordination, because there are partitionings under which we don't communicate at all. The communication is there just to get the data together to answer the question. Machine 3 never had to be consulted because it had no relevant data. All right, let's look at a counterexample now. The second one is distributed garbage collection. So if you know anything about programming languages, objects can refer to each other. And you may get to a state where you've deleted some pointers, and there are objects that nobody refers to anymore, except maybe a set of such objects, a set of garbage that refers to each other. Okay? And so the way you think about it is there's a root of your program, which is a node, and I want to know everything that's reachable from the root, and anything that is not reachable is garbage. Okay? So let's think about, we have these 3 machines now, and they have pointers between the objects. So we can traverse from the root and find all the non-reachable objects through some message passing, yeah, from some distributed protocol. And in particular, 05 and 06 are disconnected, right? But if machine 1 and machine 2 chat, do they know that 05 and 06 are disconnected? No. Maybe they're connected through machine 3. We don't know. Maybe machine 3 has no data at all. But we still have to ask it. Do you have anything that might connect the root to 05? Even if machine 3 has no data whatsoever. So even if I took all of the graph and I put it on machine 1 and the other nodes were completely empty, we'd still have to communicate. There's no way to assess the lack of a cycle without talking to everyone. And that is the key here. In the first part, we're looking for a cycle. Does there exist a cycle? Once we find one, yay, we found a cycle. Doesn't have to ask everybody. In the second case, we're saying there not exists a cycle. Or if you prefer, universally, for all, there is a not cycle, right? And universal quantification requires talking to everybody, sort of by definition. All right? And that's the whole issue of monotonicity. Monotonicity is positive. That is to say, it's existential, it exists. And negative, not exists, or for all, is non-monotone. All right? So this gives you the intuition that the math is right. So if your program in logic has not exists in it, you're stuck. You need coordination. And that's what the theorem proves. It says a distributed program P has a consistent coordination-free distributed implementation if and only if it is monotonic. The if part is easy, because it's constructive. You say, hey, you have a monotone program? Can I think of a distributed way to do that without coordination? Yeah, you just run it, kind of. It just works. The other way around is hard to prove, the only if. Okay? And a gentleman named Tom Ameloot, who is a grad student in Belgium, did this as his thesis work. So the if part is easy. I'm actually not going to dwell on this a lot. Well, actually, since I won't get into much of the next part of the talk, let's go through it. Message receipt on sets. Remember, we had sets of input, sets of output. So if you get more to a set, that's just set union, right? You merge more stuff in, that's set union. Clearly, set union is associative, it's commutative, and it's idempotent. Commutative, meaning the objects can come in whatever order. Associative, meaning they can come in whatever batch sizes you like. Idempotent, meaning if you get an item twice, it doesn't matter. Right? Well, that's clearly going to be insensitive to things like message ordering and message delay by definition. Right? So maybe we could write our programs to be like that. Well, the mathematical structure that is an object with an associative, idempotent, commutative merge function is called a lattice, or really technically it's called a joined semilattice. Okay? And people have proposed programming this way for decades. So Hector Garcia Molina's, I think, first work was on sagas, is 1987, proposed this in a transactional setting. Just write your transactions as associative commutative idempotent tasks, and then you can have these transactions that don't need coordination. Folks in the database community started talking about ACID 2.0, which is sort of a joke, or a pun, I should say, where A stands for associative, C stands for commutative, I stands for idempotent, D stands for distributed. Okay, and then there's been kind of a rebirth of this in the distributed systems community. They call it CRDTs, which are basically abstract data types that are commutative. Okay, the problem with all that is like, that's nice. Thank you for telling me to program my programs to be associative, commutative, and idempotent. That sounds hard. Now what? And the answer to that hasn't been very helpful from any of this literature. So what we did is observe that observe that you can map from one of these lattices to another. So we do this in database queries. I asserted earlier that group by in a database requires blocking. It requires us to stop because it's non-monotone. Checking that the count is exactly 5 is actually non-monotone. Checking that the count is greater than 5, however, is monotone because it's not true for a while and then it becomes true, and the more information you get, the truer it gets, right? The problem with count equals 5 is it's true for a minute, and then if you get new information, it becomes false, and you have to retract it. So if you're in a database system, there's an optimization you can do. If you have a group by followed by a having clause with a threshold, and you know that more information is going to get you over the threshold, you can do that streaming. All right? You don't need coordination. And the reason for that is you're essentially doing a morphism, not an isomorphism, a morphism from the set domain, which is a lattice, to the increasing integer domain of maxes, which is a lattice, to the Boolean domain of false becomes true, which is also a lattice. And so when you think about this, you can start to imagine little simple building blocks of lattices, sets, maps, integers, thresholds, that you can compose to build programs. And the composition allows you to build programs in a sort of more usual way, where you start with simple pieces and you put them together. But the type system and the rules of transformation guarantee the monotonicity and the lattice properties throughout. And so you can compose these lattices into bigger lattices using this composition. And the Bloom language is essentially what we call disorderly programming language. It doesn't care usually about order unless you tell it to. So very different from Java, which is all ordered. It's based on compositions of essentially logic programming, which is set lattices, and then user-defined lattices of the sort we just described. And so it's composition of Lego blocks. It's checkable. If we were to stick around for another half an hour, we'd see it again, but we won't see it again in the talk. Anyway, Bloom was a very interesting language. I'm going to just give you a highlight of the last two boxes here, and then wrap. So Anna is a project we did at Berkeley to build a very simple key value store entirely built on lattices that provides actually very rich consistency. So Anna's a key value store that, even though it's eventually consistent, actually can guarantee causal consistency. It can guarantee repeatable read transactional consistency and a variety of other consistency models. And this is all delivered in a package that is faster than anything out there. So it's 700 times faster than the leading research system, which is Mastery. It's 10 times, and it auto scales from a single box multi-core to the cloud across data centers. So it beats the pants off of Redis on a single box, and it beats the pants off Cassandra at scale, and it auto-scales itself from one to the other. Okay? So this is a very efficient, actually fairly high consistency, and very richly auto-scaling key value store. And there's really nothing quite like it. It's 500 times faster than DynamoDB's auto-scaling system for the same cost. Right? And it's not because DynamoDB is overcharging you by 500x. I mean, it's because we don't do any coordination anywhere in the system, not even across threads. There is no shared memory anywhere in the system. There are no atomics anywhere in the system. There's no test and set. There's no locking. There's no two-phase commit. None of that. It just goes. Everybody stays in their lane and goes as fast as they can. So it's a very cool system. We've had a couple of papers on it. I encourage you to look at it. What we're building on top of it is essentially a serverless environment, which we haven't named yet, so I called it System B for now. Oh, and it's crazy, Anna's crazy fast, and it scales beautifully. So this new platform is essentially like a serverless environment on top of Anna. So Anna provides the auto-scaling, and then we just put function servers on top of Anna, which are single node sort of entities. Think of them as like actors, if you like, or they're just function servers. And they sort of put their state in Anna and communicate via Anna. Everything is kept consistent through Anna's distributed consistency. So you can have causal consistency of your state. across this platform, and it'll grow and shrink over time, but you're just writing functions in Python. Or, if you like, you can get richer and you can start writing distributed programs in Bloom plus your Python functions. So it's going to be a kind of polyglot thing. We're also going to try to support other programming models like the Ray model we have in the lab at Berkeley. But it's crazy auto-scaling and crazy low latency and efficient. And it removes those statefulness and networking bottlenecks that we talked about in the current serverless world. So, summing up. Lessons. Cloud programming is hard, but serverless is too weak of a step. So if we're going to solve cloud programming, serverless is not going to get us there. Okay, we're going to need to do more. So what more can we do without coordination? I want stateful serverless, but I don't want to pay for coordination. The Calm theorem actually answers this question. It tells us what we can do, and it's quite a lot, actually. Of course, if you need coordination, you can call out from Lambda or one of these things to a zookeeper or a chubby or whatever you want. And that's true today with the existing Lambda, but you don't have to do it very often. All right? You can do what Hamilton said, which is you keep it in the corner and you use it very rarely. You do everything you can in the high performance, stateful serverless environment. So we try to keep calm and enable statefulness. And we have these experimental systems. The ANA KVS is pretty mature now. You can have a look at it. System B is being built above it. And hopefully we'll get these richer programming models and start to really look at, well, how do people program this? Not just what are the system internals. OK, so additional reading. The CIDR paper that caused the stir is in this link, and I'll share the slides, I assume, with the conference. Or you can Google for them. There's a number of papers on Bloom. The Logic and Lattices paper may be closer to the reality of the system. The Bloom website is still up, and I have students who've used it. It still works, but it's not being supported. You can read about the Calm theorem in a sort of introductory article that we've sent off to CACM, which is at Archive. And you can read about the ANA KVS and its autoscaling as well. All that stuff's published. OK. So we're going to do joint questions?
Yes. Thank you very much.
There you go. There he is. Okay.
And you can either take them from there or the microphone, as you choose. Any questions for these very interesting speakers?
So ANA sounds really interesting. What are the chances that it will grow up and escape the lab?
I'm sorry, I didn't.
What are the chances that ANA will grow up and escape the lab? And
so I guess what I'd say is the students who worked on ANA are also the ones working on this system B, and they're fairly entrepreneurial. But it's going to be up to them. You know, it's sort of, this is, I already have a startup company. I'm fully employed in 2 jobs. So
well, I guess I didn't mean you yourself, but if you look at the if you look at the history of the previous lab,
right.
There was what 14 things that were invented and 2 got out, ish. Mm-hmm. If you had to bet, would you say that this is one of the ones?
You know, the reason stuff got out of the last lab was because a couple students and faculty really pushed. And that's how it happens. So I guess all I can tell you is when I look at the profile of these students, I think this stuff will. Mm-hmm. But we're not running it as a community project right now.
Okay.
Yeah.
So one question I had about Google ML is if this is just using normal SQL underneath, why is it special for BigQuery because of BigQuery's characteristics, or can we put this on top of any other SQL database?
Do it. Is this working? Yeah. No, that's a very good question. No, I think one of our contributions here, and we do call this out in the introduction in our paper, is that what we've shown is that you can enable sophisticated machine learning functionality in any database, purely client side. So yeah, I mean the database customer can enable machine learning functionality for him or herself without having to coordinate with the database service provider.
But are there ways in which it works particularly well on BigQuery because of BigQuery's characteristics?
For sure. So since we have the opportunity to do so, we were able to enable many optimizations that make it work better. But if you like, you can do everything purely client side.
Yeah. So I would think that some of the dot products and things like that are going to be much better if your database is implemented in a particular way.
For sure, for sure. And also some of the special cases we can handle, certain problems can be solved much faster, but that does require like getting into the guts of the database.
Okay, now that stimulated some more. Let's start here.
The question is also for BigQuery. How do you manage feature management in terms of adding or removing features? Do customers have to do that, or the database facilitates that? And the other question is, if you do that, how is the layout? It's on the same tables, it's a separate table, and then people have to do joins?
Yeah, I think you're asking what kind of support do we offer for feature pre-processing, maybe? I think that's what you're asking. So one philosophy we had when developing is that we think SQL is already pretty good at doing the kinds of things that one needs to do when doing feature pre-processing and data cleaning and filtering and that kind of thing. So we leave that, currently we leave that in the hands of the analyst and his or her SQL skills to sort of do themselves. I think we have more stuff along these lines coming up, but I've been told I can't talk about it. So I think next week you'll hear some announcements.
So just to clarify, sorry.
Just to clarify, the question is...
Okay. There you go. Yeah, there you go. So the question is about if an analyst wants to add a new feature, for instance, to, let's say, a very big table, do they add a column to the table? Because that's actually, SQL is not very good at that, right, at adding a full column.
Yeah, I see what you mean. Yeah, I would say that kind of problem is currently out of scope for this project. Yeah.
This is a question to Joe. So I was wondering, is because of the your approach, looking at a language-based approach, are basically all existing systems out of luck? Do they have to be re-implemented, or do you have some thoughts about how existing storage systems would take a long time to build and to get accepted sort of as a reliable system? Do they have any chance to be refit into your model?
Very interesting question. So let me try to answer it in two different places. One is at the language level, so at the programming language level. So there's very suggestive work. For example, my colleague Alvin Chung, who we're bringing to Berkeley from Washington, in doing program synthesis to translate Java or other legacy programs into batch languages like SQL, MapReduce, and so on. So he's done this translating fragments of Java to SQL, translating fragments of Fortran to Halide. So he's done this in many contexts. If you can lift your old legacy code into a more amenable language framework, it doesn't really matter what the language is, it's the internal model, then you can do things perhaps like assess the monotonicity of the implementation. You're still, and you remove some of the implementation actually, because you go to a higher level spec. And then if someone built something that maybe is sequential, you can say, oh, well, there's a non-sequential algorithm for this task. So I think that's very exciting. Like a lot of sort of legacy code conversion things, it's you ask the question of whether it's the right thing to do, but it might be at this point in time, given that people are so devoted to, it's so hard to transition people out of sequential programming. So I'm excited about that. It's absolutely research, though, with a capital R. At the system level, at the storage level, which I think you pivoted your question to kind of halfway through, some of the work we've done in the lab is to bolt better consistency models onto weaker storage engines. So for example, in Peter Bayless's thesis, we bolted causal consistency on top of Cassandra. And you can do that. And you could do it actually, now that we've been through the Anna experiment, you could do it more elegantly using lattices. And it becomes feasible. So some of the kind of infrastructural things that chose weak consistency can be upgraded to a degree. And I think Cassandra actually even has user programmable merge functions. The best example of this was React, which was the open source KVS from Basho, but they went out of business, unfortunately. But they were doing lattices as their merge functions. They had drunk the Kool-Aid. The other direction, if you've built a transactional store untangling the transactions from the transactional store is very hard. Folks at Microsoft probably are doing the most interesting work in componentizing a transaction system into subsystems and being able to deploy them, say, on different nodes, so you can auto-scale the read-write piece without having to scale the transaction manager piece and so on. So there's been some nice work there. I would say they would have a better time of it than taking, well, in their Azure stuff than maybe in their old SQL Server stuff, right? Untangling a transactional storage system, at least all the ones I've lived with, I think is not practical. But again, you could pay people, experts, to do that. So in some sense, that's fine. It's like if we have to rebuild storage engines, we will, because we can, because we're great programmers. If we have to change the way that general purpose programming is done in the community, that's actually the harder problem, right? So I'm less concerned about the storage engines.
As you know that there is a move towards edge computing, fog computing. And many in the community, including us, Okay. So there is a move towards edge computing, fog computing, and the pendulum swings back and forth between, as it has done before. It's still out in the horizon, but many of us are having more and more success in, trying various applications on massively distributed edge computing kind of paradigm. Have you, A, given thought to it, and B, how does either these problems or these the models that and the platform that you're offering might scale to a more distributed edge computing kind of paradigm?
Great question. So generally speaking, anything coordination free will scale beautifully to an edge computing environment. You need to almost do it that way. I'd also point out, one thing we learned along the way, in fact, from the Hacker News brouhaha about our paper, one of the more constructive comments there was, hey, Cloudflare's cloud workers, which are essentially edge computing programming for CDNs, are much better than Lambda and the like. They provide more of the functionality you're looking for. So the edge computing community, at least as represented by the content distribution networks, are thinking about these things, I think, in a more extreme way than the cloud vendors have been, and I think that's good, because it pushes you in the direction you need to go, which is coordination freeness when possible. And as to sort of really edge computing, I mean, just for the record, we were doing that in my group at Berkeley with, TinyOS and TinyDB in the early 2000s. So absolutely we've thought about it. And this whole line of work actually grows out of having been through that experience and realizing that network routing and query processing are very coupled. And that when you start to think about routing protocols as queries, you can optimize them. And when you start thinking about everything as queries, you get programming languages that are less sensitive to sequential computing. So this whole thing actually was born out of our experience of trying to do stuff with very distributed, very low power sensors. So it's very astute to ask your question. It's really, in some sense, the genesis of this 15, 20 years of work. Started in running queries on tiny little sensors.
In terms of load distribution, server allocation, the various things that go on in cloud server today, how easy or difficult will it be? And I'm not talking of just sensor node based IoT kind of computing. I'm talking of edge computing where the edge, these are more powerful edge nodes, cloud nodes, but located at the maybe at the mobile cloud base stations maybe, or maybe one day even on the street lampposts also. So they are closer to you for ultra latency requirements, and yet you have to have all the database, all the the server allocation functionalities, all those things done. And there might be different kind of conflicts and conflict resolution issues there.
Great. So I have thought about those things. It's a long conversation. I think maybe what you're alluding to is, program semantics aside, because I didn't say anything about the sizes of nodes or any of that. When you think about resources, there are sort of hidden dependencies. For example, you want to use all the memory on the box, and I want to use all the memory on the box, and we can't get off the box. That creates an implicit conflict, even if there's no semantic conflict, right? And so these things do crop up kind of under the hood. beyond the programming model. That's always interesting. There's lots to talk about under the umbrella you raised. I guess my high-level view of this stuff is once you're in the realm of scheduling and resource allocation, usually simple things are the best answer, and usually engineers find them, and it all works out. And it's not as hard as it seems up front. It's just like over and over, you go to these fancy operating systems talks that have like some very involved scheduling algorithm, but that's not what people use in the field. What they use in the field is maybe for 10% more resource consumption, you get a simple, stable algorithm you can manage, and it's something like, first come, first serve, or, some variation of LRU. A lot of these engineering problems get solved with relatively straightforward solutions. The other thing I'll share is that when we were doing the TinyDB, TinyOS work, and I was really excited about, we'll have queries running on battery-operated devices on every leaf of every tree, right? That was really literally what we were going after. Well, they didn't have leaves, but we had these sensors up in redwood trees, and we were measuring like how the tops of the trees moved in the wind, because that's what the scientists wanted to know and stuff. The thing is that like, even back then, but certainly today, battery-operated things, where you're not tethered to power, have extremely low bandwidth. So they just don't generate very much data in order to preserve their lifetime. Because network communication, radio is expensive, okay? Anything that's got power is either on the internet or super close to it. And so you usually have a gateway node nearby that's got power and an Ethernet cable, and then you're done. Then it's just plain old distributed computing again. So a lot of our ambitions to do crazy new things in this environment were a little bit squelched by the fact that it was rather niche-y, the cases that were extreme. Most cases were not extreme. They were powered and wired, or at least Wi-Fi, and then it's pretty conventional. And so that's something to keep an eye on, is like, how fancy does this need to be? Having been burned by it once, I'm sensitive to that.
Okay, let's thank all of our morning session speakers, and I think lunch should be served outside.